hi everyone. Thanks so much for coming to this talk. And thank you, Don, for inviting me to this wonderful session. I'm glad to be back to NISQ and see some familiar faces. Very nice weather today. You can actually see the Golden Gate Bridge, which is quite rare. And so, yeah. Just before I get into the main slide, I want to just introduce myself. As Neil said, it's just my background. And today I'm going to talk about this internship project that I worked at NISQ with Jan, Reva, and Don on studying quantum algorithms for solving PDEs. And this is my email address if you want to reach out. So this is how the talk will be structured. First, I'll talk about some background and motivation for solving differential equations on quantum computers. And then I'll set up some terminology and tools needed to implement them. And then finally, I'll go over our main contributions of this project, which is working on the implementation of these algorithms for solving PDEs and running both numerical simulations and experimental runs on the IBM hardware. So just some background, as you probably already know, so maybe it's kind of redundant. Quantum computers offer envisioned to offer numerous promising advantages and applications in various fields, and one of which that we focus on is solving differential equations such as ODEs and PDEs. And one way that quantum computers are advantageous for solving, say, PDEs is that information can be stored more efficiently in quantum computers than in classical computers, since quantum computers can require just exponentially fewer qubits than bits for storing the same amount of information. So this is one of the things that we will take advantage of in this project. And as highlighted, the focus of this talk will be on solving PDEs on quantum computers. So one natural question to ask is why do we even solve PDEs in the first place? Well, PDEs are quite ubiquitous in our world. They describe a bunch of different phenomena, all the way from fluid dynamics of the ocean waves to just the sound waves of guitar strings. And in the past couple of decades, there have been many proposed approaches and algorithms for solving PDEs on quantum computers that promise some sort of speed up over classical computers, either through just better complexity scaling or just more efficient storing of information. And in this talk, I'll focus on this recently proposed algorithm by Lubash et al. That uses the Fourier space using the quantum Fourier transform to solve specific linear PDEs. So the goal of this project is really assess the near and long-term advantages of quantum computers for solving PDEs, and we'll focus on this particular implementation for that. So just a very key, brief summary of the main part of our project. So as you can see, this is the title of the talk. We reference a prior work by Lubash et al. And for solving PDEs using quantum Fourier transform. And a major contribution of our project is that we explicitly implement these algorithms, compiling various techniques. And so we translated from just theory to actual implementation applications on the quantum computers. And this is the basic workflow of the algorithm. So you start with some initial state psi of 0, and you use this operator. You probably already know the QFT, the quantum Fourier transform, the inverse, and you bring it to Fourier space. And in this case, it just makes the problem simpler for specific PDEs. And then we use this evolution operator in the middle to solve this equation, and then transform it back to the real space, and then you get your answer at time t. And as laid out in this paper, we use two different levels of approximations. One is SAA, which is the small angular approximation, and the other is the QSVT, which is the quantum singular value transform. I'll define these terms later, but to highlight that we use two different approximations for implementing this middle evolve circuit, and then we do an implementation of this and then compile it and put it on some IBMQ hardware to run our algorithms. And the sort of PDEs that we solve are the very simple linear PDEs. So we have some vection equation, wave equation, cosine equation. So we use these circuits in A and then solve PDEs in B. And then the other main part of the project is then we benchmark these algorithms with both numerical and experimental runs. Okay, so this is like the main crux of our project, and the rest of the part will be just digesting each part and how we go through that. So this part will go on like terminologies and conventions that we use and tools that we use to solve the PDEs on the quantum computer. Don't worry too much about the details, just so that we're on like kind of the same page. So for our system, we just consider one-dimensional functions, psi of x. So there, x is some spatial parameter, and this function is defined symmetrically about 0. So we set x to be between -½ and 1/2. So for example, the psi of x could just represent the sound waves of your guitar strings at a specific time t. And then we discretize the space into equally spaced big N equals 2 to the small n grid points, where we'll see that the small n corresponds to the number of qubits. And the grid points are indexed by this j, which goes from 0 to big N minus 1. And x sub j is the actual x values of your grids. And then we use amplitude encoding to encode the function into a quantum state with binary representation. And so we use these computational states, ket j, to do this. And so just a quick example. Let's suppose that we have a grid of 4 points. So we have 2 qubits here. We have the x-axis here, and we have 4 equally spaced grid points. In this language, the leftmost is indexed by j equals 0, and then the rightmost point is indexed by j equals 3. And this is also represented by the state of your qubit. So the leftmost point is represented by the 0, 0, and then so on, and then until the rightmost is represented by the first qubit being at 1 and the second qubit being at 1 as well. And then the amplitude encoding part comes in, where we represent this quantum state psi in this linear superposition, where the amplitude in front of each basis state just depends on that function value at that grid point. So, for example, the lastmost, this 1, 1 is the lastmost grid point. So the coefficient is just the psi, your function at that grid point, which is at x sub 3. This is how we encode our state, state into a quantum state. And then finally, one last thing is that we use the quantum Fourier transform. This just some definitions of what we use. So we take the quantum Fourier transform that has a different kind of basis states. It just has a different notation represented by k. And our definition of quantum Fourier transform is that it takes this k and it spits out the j basis states that we had before. And this is actually the shifted quantum Fourier transform, where this k, shifted k, this tilde k shifts the k from, instead of going from 0 to n minus 1, it does asymmetric around 0. This is just a peculiarity of how we defined our function. We defined it to be symmetric around 0. And so this is just a extra detail here. And for example, this is what the shifted QFT would look like for 3 qubits. This middle part is just the normal QFT you're probably very familiar with. This just shifts the axes of your spatial and your Fourier bases. And this is just a representation of what that shifted k, which is our wave number, looks like as a quantum operator So that's just all the details here. Now we can actually go into the algorithms. But one important thing about these quantum Fourier transform is that it diagonalizes your differential operators. This is what we'll be using, what we'll be exploiting for our algorithms. So for example, if you have your first order derivative of psi at point x sub j, in some first order approximation, that function depends on your value at x sub j plus 1 minus x sub j minus 1. With some algebra, it can show that the differential operator here can be written in this form where you sandwich two QFTs and inside you have a diagonal operator in the Fourier basis. So for example, on the left, a matrix representation of this function may look something like this. This is because at each point, your value depends on point on the right and the point on the left. But when we use this notation, you can see that in Fourier basis, this operator in the middle is diagonal in Fourier space. And then we'll use this, exploit this nice feature to simply solve our PDEs. And the same is also true for the second order derivative here. So the second order derivative is also diagonal in the Fourier space. That's all the terminologies and tools that we needed to solve our PDEs. So let's just go into some real examples. So first example we consider is the vection equation. So the vection equation is given by this PDE here. It's a very simple linear PDE where you have the time derivative of psi is equal to negative r times the spatial derivative of psi. The vection equation models the bulk movement of fluids. And so this r term is kind of the speed of that bulk. And here's an example of what that would look like. So this is at an earlier time, and you can see that psi just moves here to the right as a function of time. So here's the actual main kind of thing is that when you represent this function, this PDE in quantum language, we once again here we use the derivative operator in this new representation, and you can actually see that to just solve this, you just need to exponentiate the thing in the middle. So the solution to this PDE is that the function at time t as a state is just exactly represented by this equation here. If once you have the initial state psi of 0. So the very cool thing about this thing is that this does not depend on this. You get an explicit circuit regardless of your time. So there's no need for any sort of like toroidalization. And so now the question is, how do you implement this operator in the middle? And so there's two ways to do this. And one way is just to use the small angle approximation, where you approximate the sign as approximately equal to the 2 pi k over n. We assume that your wave number is small. And in this case, this operator is just given by a product of a bunch of these exponential operators. And in circuit diagram language, this is just a bunch of single cubic gates. So this operator in the middle, the sign of 2 pi k over n, you can approximate as a series of single cubic gates. So here we have just small n number of gates. And the angles, the rotation angles of each gate is just dependent on your time t. So you have a explicit circuit for solving this equation at any time t. You just need to change the rotation angle of each single cubic gate. So this prevents the use of the need for toroidalization. Okay, but what if the small angle approximation is not quite accurate enough? we'll see what we mean by that. But let's say for some certain applications, this small angular approximation is not accurate enough for our problem, then we can actually directly just implement this operator without having to use any approximations. And to do this, you can see that when you use the discrete Fourier transform of this operator, it's given by some sum of series, a series sum of these exponential operators with some complex coefficient C of m. I don't show the exact expression for C of m here, but just know that the C of m is exactly derivable just from the parameters. So you just use, you don't need any quantum computer here to get C of m. It's just exactly just from the PDE. So this kind of feels weird. Why do we do this? It feels like we haven't actually done anything, but thankfully we can actually implement this using the quantum singular value transform. So that's the QSVT. That's the main part of the title here. So the basic idea of QSVT that we want to construct a circuit that can implement P of U, where P is some complex value polynomial and U is some unitary operator. So we'll use QSVT to implement this P of U, and is doing a polynomial transformation on our unitary. And we'll see that once we have this set up, we can implement the series sum that we have before. So to do this, we need to find some complementary polynomial Q that satisfies this condition. We use this paper by Yamamoto and Yoshioka to implement this numerically. And then the basic circuit that does this is based on this paper by and reference number 2 from the paper titled Generalized Quantum Signal Processing. Basically, the details don't matter too much here. The only thing that matters is that you need an extra ancilla qubit, and you need to do control unitaries the same number of times that you have terms in your series. And once you have that, once you have this circuit, and you measure your ancilla, if the ancilla qubit is at 0, then according to this setup, this theorem, the bottom half is your P of U that you wanted. So we also implement this on Qiskit and run it as well. And so basically what that means is we had this exponential operator we want to solve. We use Fourier transform to represent it as a series sum. And then we use QSVT to put it in this form, where you're doing a polynomial transform of this unitary operator U, and where U is just e to the I 2 pi k over n. So in circuit form, this looks something like this. So remember, we need to do a control unitary here, big N number of times, because that's the number of times this appears in the series. And each control unitary is a bunch of entangling gates. And here we have small n plus 1 entangling gates. So it gets quite expensive. We'll see that it can achieve more accurate results even on quantum hardware, even though here we clearly have a much worse scaling, because previously we only need a single qubit base. Now we need a bunch of entangling gates for our evolution circuit. So here are some simulation results. This is firstly just doing some state vector simulations. We use 6 qubits. So remember, for QSVT, we have an extra ancilla, so there's 7 qubits. And we initialize as a Gaussian at 0. And then we just evolve as a function of time. And the bottom panel, for each plot, we're plotting the real value of our function, because we start with a real value function. And each bottom panel just looks at the difference between the classically derived solution and the quantum solution. And here we're looking at both the single small angle approximation solution and the QSVT solution. And you can just visually see looking at the bottom panel that the QSVT based solution is much more accurate than the SAA. But on the other hand, SAA uses only 30 entangling gates. That's all from the QFT, the quantum Fourier transform. Meanwhile, the QSVT based solution uses way more entangling gates here. But we'll see that this is not too bad if you go into smaller qubits and try on hardware. So that's the evacuation equation. And just to breeze through on the next equation, we have the Poisson equation. An example on the right here. Here, rho is some source term, and the Poisson equation usually used to model some electromagnetic wave, and so a field, and so the psi is just our signal. And we used a similar setup. We have our PDE on the left. We represent it in quantum language on the right. And then the idea is once again to implement this middle operator, and we use QSVT again actually. Here the coefficients are slightly different from the previous one, but the actual unitary that we use is the same. So it's the same control unitary that we had before. But in this case, the only difference is that these coefficients C of n is different from the evacuation equation. And then we did the same thing. We just tried out 4 different types of source terms. So some peaks, Gaussian, some composite sines, and a ramp. And here we only use QSVT, so we just have the classical solution and the quantum simulation solution with QSVT. Here, QSVT solution is we're using state vector simulation, so it's just accurate up to machine precision because we're just doing an exact implementation. Same number of entangling gates, but just the way this coefficient C of m changes, it requires exponentially many shots. So it's not quite as good as the evacuation equation. So finally, we tried out this algorithm on IBM Q QPU. In this case, we're constrained by noise, so we only consider 3 qubits. So that's 8 grid points. And then for the QSVT based solution, that will use 4 qubits because we have n+1. We have the extra ancilla. And we initialized the function as a Gaussian once again. And we ran like 10,000 shots on IBM Q's Kingston device. And here's what the results look like. So the solid orange line is just the classical solution, just using a classical ODE solver. The blue circle is the quantum hardware results using the small angle approximation. And then the black square is the quantum hardware results using QSVT based solution. And on the bottom panel, we're measuring once again the difference between the classical and the quantum multiplied by 100 just for visual clarity. And you can just see that more visually, but also quantitatively, that QSVT based solution is more accurate than the SAA, even on this quantum hardware. And in this case, the SAA solution used only 21 2-qubit gates after transpilation, but the QSVT solution used 50 2-qubit gates after transpilation. So to the best of our knowledge, this is the first time that QSVT was implemented to solve PDEs on a quantum computer and achieve better results than the one without it. So pretty exciting for us. So that's kind of the end of this talk. So here are the key takeaways. So this is the workflow that we had before. We identified some promising quantum algorithms for solving linear PDEs as laid out by Lubash et al. And we developed and compiled a numerical implementation of these algorithms and verified their validity. We experimentally ran the algorithms on IBM Q device, specifically for solving the evacuation equation. And we verified that the SVT-based solution achieves more accurate solutions than the small angle approximation one, just for solving the evacuation equation. And so for future work, we want to extend to obviously larger qubits on the experiments and potentially solve the Poisson equation for a more physically relevant source term. I was previously just using some random random sources that I could think of, but maybe we could just use it for actual physically relevant ones. And with that, I would like to thank my mentors, Reva, Jan, and Don. And thanks for NISQ and LBNL for hosting me during the internship and inviting me. And thanks to QCAN for providing me with the quantum computing access. Thank you for listening.